Hello dear student, I am Monur Islam. Today in this video we are going to discuss an important question of complex analysis. This question was asked in CSIRNET June 2021 20 papers. And it is question ID 529. Okay, this is basically a question from part C, and it is 4.7 right mark. So let's discuss the question briefly. In the question there is a function given f z equal to sin z to m by 1 minus cos z, where m and are natural number. Okay, positive integer means natural number. Then it asking z equal to 0 is a remote singularity, pole is singularity. Okay, so we first of all we have to familiar to this term. What is remote singularity, what is pole, what is essence singularity. Okay, after this we can solve this question easily. Okay, to solve this question I am first giving a concept regarding to this question. Okay, so that if in future exam any question come to in these topics we can answer easily. Okay, our aim is not to solve this question only, our aim to solve this question that came in future also, that we have to solve only that we can solve also. Okay, so let's start. First of all, we need a result. It's called Laurent expansion. Laurent expansion of a function. Okay. Laurent expansion of a function. Laurent expansion of a function. It is not so. We need Laurent expansion of a function. Okay, suppose you have a complex function you have a complex valued function. Okay, is the form a plus ib is complex function. Okay, define on region D, and D is the endless region. Endless means like this, in the axis center is around radius circle, center in another r2 radius circle. Okay, this means this. Let f be a is a complex function and define function, and this function is defined on D, and D is the endless region. Okay, you can write the endless region as like you can write define on, I'm directly writing r2 less z minus alpha less r1. Okay, alpha is the center, you can write here. Okay, then each point on this endless region z, then for each point on this endless region z, you can represent fz as a power series. Okay, and this power series I am writing. Okay, for each point fz in endless region, for each point in the endless region, alpha center circle r1, the r1 radius, it r2 radius. Okay, and for each point in the endless region you can write fz like a series form, summation n equal to 0 to infinity in z minus alpha whole to power n. Okay, and second part is n equal to 1 to infinity bn z minus alpha to minus n. Okay, where n bn has expression n equal to 1 by 2 pi I integration c fz dz z minus alpha to the n plus 1. Okay, n varies from 0 1 to so on. Similarly, the expression of bn, if bn is nothing but a minus n. Okay, you can say bn is nothing but a minus n, and bn is nothing but a minus n. Okay, I am not going to this. I we need I'm going to this that we have need. Okay, then it is happen then when alpha is said to be pole, alpha is said to be removal singularity, alpha is said to be singularity. Okay, with this series. Okay, so in this series, if all bn are 0, okay, if all bn are 0, then we say this alpha is a removal singularity. This alpha is a removal singularity. Okay, if all bn 0, then this term only. Okay, something like n z n. Then if then this series become Taylor series, and then alpha is called removal singularity. If finally bn are non-zero, means b1, b2, b3 are non-zero and except all are 0, then this alpha is said to be pole of the function. Okay, and if infinitely many bn are non-zero, infinitely bn are non-zero. Okay, then we say the alpha become essential singularity. Alpha become essential singularity. Okay, so we understand the concept about removal singularity, pole, and essential singularity. Okay, now I am writing the result directly that we have need. Okay, I am writing a result that we have to need to solve this question. Okay, the result is this. Let's suppose alpha be a singular point. Okay, singular point means it may be a removal singularity, it may be pole, it may be essential singularity. Okay, let alpha be a singular point of fz, of a complex function fz. Okay, real one. If limit z tends to alpha fz, this is limit to alpha exist and finite. Okay, then we say that alpha is a removal singularity. Alpha is said to be removal singularity. Okay, if remind this. And this concept came in from Lorentz expansion. Okay, as you know, if alpha is a removal singularity, if alpha is a removal, then all bn have to 0. If all bn have to 0, the negative part automatically reduce. Okay, in the series form, in the series negative part pn z1 alpha to n minus n, this series is not in the expansion object. Okay, only this term left, n z1 to n. Okay, right. I am saying that if alpha is a removal singularity, then only summation n z1 alpha to n bn z1 to n in this expression, Lorentz expression, only this term left, because all bn are 0 for removal singularity case. Okay, so if all bn are 0, then we have to leave this series also. Okay, only this series. Now if you take limit z tends to alpha, this become a finite quantity. Okay, this limit exists and this gives a finite quantity obviously. Okay, I think this gives a0, because other term quantity z1 alpha factor, if you take limit z tends to alpha, then this term becomes 0. In case a1, it will be factor, it will multiply by factor z1 alpha. Okay, if you break this, you get what? A0 n equal to, if you break this series, you get a0 plus a1 z1 alpha. Okay, a0 plus a1 z1 alpha, and so on. Each term contains z1 alpha factor. Okay, so if you take limit, then this term becomes 0. Okay, this term also, limit term goes 0, only a0 left. Okay, so this becomes a finite quantity. So if alpha be a removal singularity, then limit z tends to alpha fz always a finite quantity, it exists and finite quantity. Okay, now if alpha be a, alpha is said to pole, alpha is pole, if limit z tends to alpha fz will be infinite. Okay, alpha is pole if limit z tends to alpha fz is infinite. Yeah. This also came from Lorentz singularity. If you observe the Lorentz expansion, you observe the Lorentz expansion, observe what is Lorentz expansion object? This summation n z1 alpha to n, here n varies from 0 to infinity, here summation bn n varies from 1 to infinity, z1 alpha to minus n. Okay, we know that if the alpha is pole, then in this case this is contain finite term. Okay, means suppose it have b1 z1 alpha, then b2 z1 alpha the square, and the term suppose b3 are 0, then only this term left. Okay, and this will become n z1 alpha alpha to n summation n equal to 0 to infinity az. This will become, I assume that b3 bn are 0 for bn are 0 for n. I am assuming that bn are 0 for n3. Okay, if it fall, then it series may not be go to infinite. It stops somewhere. Okay, so I am assuming that bn equal to 0 for n greater than 3. Then now see, if you take limit in this expression a z test to alpha, then it gives a finite quantity. Okay, gives a0, and it gives infinite, it gives infinite. So overall limit goes to infinite. So overall limit of this expression goes to infinite. Okay, if alpha is a pole. So I am saying that if alpha is a pole of fz, then always limit z to alpha fz is infinite. Okay, but if alpha is a essential singularity of fz, then limit alpha is equal to fz if limit z to alpha fz does not exist. Okay, this limit does not exist. If you observe the Lorentz expression, you easily understand this. Summation n z minus alpha to n summation equal to 1 to infinity bn summation equal to 0 to infinity n z minus n bn z minus alpha to minus n. Okay, in this case of essential singularity, then this series contains infinite term. Okay, now if you take limit, this gives a, if you take limit s z tends to alpha. Okay, alpha, this gives infinite quantity a0, but this gives infinite limit. Sorry, this gives limit doesn't exist because it contains infinite term in power of negative power of z minus alpha. Okay, infinite term. So if you take limit, in this case for this part limit does not exist. Z tends to alpha, limit doesn't exist. So if alpha is a, so I can say that if alpha is a singular point of fz, then if limit z tends to, so I am combining all the cases. Okay, so I can say that suppose alpha be a singular point of fz, of a common function fz, then alpha becomes a removable singularity rs if limit z tends to alpha fg exists and finite. Okay, this exists and obviously finite. Okay, and if alpha is a pole, then this limit z tends to alpha fz, this infinite. Okay, and third, alpha is essential singularity if a limit z tends to alpha fz does not exist. This limit does not exist. Okay, so using this result we are going to solve this question. Okay, and it is very easy to solve the question using this concept. Okay, if alpha is a singular point of fz, then alpha is said to be removable singularity if z tends to alpha fz is infinite. Alpha is a pole, z tends to alpha fz is infinite, and alpha is a singularity if z tends to alpha fz doesn't exist. Okay, so using this concept we are going to solve this question. Now see, if you observe the question, it is given the relation between m and n. Okay, each option gives a relation between singularity if m greater than n, pole if m less than n, m less than 2n, pole if m greater than, or m pole if m greater than 2n. Relation between always gives a relation between m and n, m and 2n. Okay, where m and n are positive integer, means natural number. Okay, m are natural number. So what I am doing, see, it is given m and n are natural number. Okay, m and n are natural number. Now see, you can tell me if m is a natural number, then obviously m and 2n is a natural number. Okay, I'm not doing anything, I'm just multiplying n by 2. I'm just multiplying n by 2. N is a natural number, then 2 and 2 it multiple 2 is also a natural number. Okay, so then it is the m is a natural number and 2n is a natural number. Then in this 2, what can be relation? In this two natural number, what can be the relation? Either in this natural number there may be 3 relation. Okay, either first of all m may be greater than 2n, second m may be equal to 2n, or third m may be less than 2n. Okay, this case, this three relations are possible. Okay, otherwise no relation are possible. Because m and 2n are natural number, then only three relations possible, either m greater than 2n or m equal to 2n or m less than 2n. Okay, so we now I am first consider the case m greater than 2n and see what gives z equal to 0, either pole or dimensionality or essentiality. Okay, so see, I am considering the first case, case 1. Case 1 is, name it case 1. Case 1 is m greater than 2n. Now see one thing, m is a natural number, 2n is a natural number, and both are natural number. Okay, it greater than 2n, m is greater than 2n. Okay, so you can assume like this, is 2 is 1, 1 is a number, 2 is a natural number. Okay, so between there is a gap, so gap is 1. So it's again 3 is a natural number, 2 is a natural number, between 1 and 3 there is a gap, between is 2. So any natural number there is a gap between either, this gap may be either 1 or more than 1, and the gap is a natural number, the gap value is also a natural number. Okay, so I am using this concept. Since m is a natural number and 2n is a natural number and m greater than 2n, so I can write m is 2n plus k. I always write where k is a natural number. It may be 1. If it conjugative natural number, then k will be 1. If it not conjugative, then k will be greater than 1. Okay, so now put this value in fz. What is fz? Sin z power m by 1 upon cos z. Okay, power m. Yes. So I am going to evaluate this limit, and you have to put m is 2n plus k. Okay, m is 2n plus k. So I am considering the case m greater than 2n. Okay, so sin z power m, m means m, I have written m equal to 2n plus k. K is a natural number, either 1 or it may be greater than 1, natural number. Okay, so write in place of m, you can write what, 2n plus k. Okay, and lower part is cos z power n. Okay, here is 2n, so I am doing one thing, square sin z and 1 minus cos z. Okay, take it power n. If multiply, then give sin 2n. If multiply, then it gives 1 minus cos z 2n, and remaining part sin z power n, and outside for k. And k is a natural number. Okay, k is a natural number, and it will be greater than or equal to 1. Now if you take limit, the limit will be divided into two parts. Okay, either the limit will be first goes to limit on this part, and second goes to limit on this part. Okay, limit is obviously z tends to 0, because you have to check z tends to 0. Here alpha is 0. Okay, so you have to take limit as z tends to 0 fz. So if you take limit z tends to 0 fz, see in this case upper part is limit as z tends to 0, because sin z square z, lower part cos 0 is 1, 0 by 0, so it is 0 by 0 form. So you have to differentiate, so 2 sin z, and sin z difference on cos z, next lower part is sin z. Okay, power is n. In this case sin 0 is 0, the 0 power is a natural number. Is a natural number, either 1 or maybe greater than 1, 2, 3, 4, 5, 6. It is okay. So it will always give 0, and it gives finite quantity 2 power n. And if you take limit z is 0, then it gives cos 0. Cos 0 means 1, so it gives 2 power n. 2 power n is 0. Okay, it gives 2 power n. It gives 0, so it gives 0 ultimately. Okay, so we have as you take limit z is 0. Okay, as you take limit z is 0, then fz goes to 0. Okay, as you take limit z is 0, right? So since fz goes to 0 as z is 0, then you can say that limit of fz is finite. Okay, limit of fz is finite. So I get that when m greater than 2n, then limit z tends to 0, fz equal to 0, fz equal to 0. Here 0 is alpha, so limit z is alpha, fz equal to 0, and this is a finite quantity. So this limit exists and finite. So we can say in case of m greater than 2n, z equal to 0 is a removable singularity, Rs of fz. Okay. Now So m greater than 2n, then if there is a then z equal to 0 is a removal singularity. Okay, now I am going to case m equal to 2n. Okay, if I conclude for the case m equal to 2n, then we can go to the option 1. Okay, it says m greater than 2n, or also third option it says m greater than 2n. Okay, so I am understand that till now I have done that. When m greater than 2n, then z equal to 0 is a removal singularity of fz. Okay, now we are going to second case. Now going to second. What is second case? M equal to 2n. And if variable, if m equal to 2n, then put m equal to 2n sin z power m. What is sin z power m? Into power is sin z power m. To put in 2n, lower part is cos z power n. Okay. Now you have to take limit z is 0. So first of all, if you write this sin square z 1 minus cos z and take limit power n. Okay, see, if you take limit z is 0, s take limit s z is to 0. If you take limit s z is 0, then is goes to 0, lower part also goes to 0, with cos 0 is 1, 0, 0 by 0 form. So 2 sin z cos z, and it becomes sin z power n. Any natural number obviously. So sin z out, it gives 2 cos z. As z to 0, cos 0 goes cos 0 cos 0 goes to cos 0. Cos 0 means this part goes to 1. Okay, so 2 into 1 means lower part is 1. 2 by 1 is 2. So it gives 2 power n. And 2, if any natural number, 2 power n is always finite quantity. Okay, 2 power n is a finite quantity, and this I can say that this limit exists. Limit z to 0 fz exists when m equal to 2n. Okay, so in first case, in case 1, we observe that when m greater than 2n, z equal to 0, z equal to 0 is removal singularity, because in case limit z to 0 fz exists and finite. And when m equal to 2n, then also limit z to 0 fz exists and finite. Then we can say m greater than 2n, and if m greater than 2n, then z equal to 0 removal singularity, and if m equal to 2n, then also z equal to 0 is a removal singularity, because in this both case limit is exist. Okay, so you can say when m greater than 2n, then z equal to 0 is a removal singularity. So option 1 is correct. It says m greater than 2n, then it is a pole. No, option 3 is incorrect. So, okay, so remaining option are m less than 2n, and there is fourth option. So I am going to the now to the option 3. Is said m less than 2n. Okay, when m less than 2n, see, we can again do the same process as we done in case 1. M is a natural number, 2n is a natural number, and there 2n is greater than m, so we can always write 2n can be made less than m plus k, where k is a natural number. It will be 1. If it is a conjugative natural number, then it will be 1. If not conjugative, then it will be more than 1. Okay, fz, write fz, write fz. From this you can write m equal to 2n minus k, 2n minus k. So it gives sin z power n. M means 2n minus k, means cos z power n. Right, now you have to take limit h is 0. If you take limit h is to 0, then this goes to, first of all you have to write this. Okay, you have to write in a proper way. I am writing this sin z, sin square z by 1 minus cos z power n. Okay, and multiply it by, there is, you have to take this power outside, so it gives 1 upon sin z power k. Okay, now as previously we have done, this limit as z to 0 goes to 2 power n. Okay, 2 power n, because upper part gives 2 sin z cos z, lower part is sin z kept out, it gives 2 cos z. At z to 0, 2 cos z gives 2 power n. Okay, so this goes to limit 2 power n for any natural number s z to 0, s z to 0. But this limit sin 0, 1 upon sin 0, z to 0 goes 0, k is a natural number, so 0 is lower side. Okay, so 1 by 0, k is a natural number, so 0 power k doesn't give any effect, it also be 0. Okay, because k is a natural number greater or equal to 1, so 1 upon 0 gives infinite, so this is infinite, so 2 power n into infinite, this gives infinite. Okay, so we see that limit z to 0, fz goes to infinite, so we can say that z equal to 0 in this case. In this case, when m less than 2n, then z equal to 0 become pole. Okay, using the result, z equal to 0 become pole. Okay, so m less than 2n, then z equal to 0 become pole. So option 1 is correct. Okay, now you can tell me, when m, we observe that when m greater than 2n, so we get z equal to 0 is a removal similarity. Okay, when m less than 2n, then z equal to 0 become pole. Okay, then any other case left, we have conclude for m greater than 2n, z equal to 0 is a removal similarity, RS. Okay, also for m equal to 2n, z equal to 0 is a removal similarity, RS. Okay, or m less than 2n, then z equal to 0 is a pole. See, m greater than 2n, m are n natural number, then m may be greater than 2n, or m equal to 2n, or m less than 2n. So m greater than 2n, then is a removal similarity. M equal to 2n, then equal to removal similarity, and m less than 2n, then is pole. Okay, so there are no any relation between m and 2n. Okay, there are no relation between m and 2n, and so there are no relation between m and n left. Okay, we conclude all the cases. Okay, so it for the same guide. So we in any case, we for any three cases, we does not get essential similarity. Okay, we always get either removal similarity or pole. So essential similarity does not arise. So 0 0 never be essential similarity. So in this question, option 1 and 2 are correct. This question, option 1 and 2 are correct, and option 3 and 4 are incorrect. Okay, in this question, correct option 1 and 2. So if you in doubt, you can always ask in the comment section. Okay, and more video solution will come in the upcoming videos, and please support my channel, and thank you so much. Thanks to all.